Well, today we start a new chapter. It's chapter 3 of aerodynamics, talking about Inviscid incompressible flow models and application to or approach to analytical solution of this type of flow. This chapter is divided in several parts. Main parts are talking about Bernoulli equation and then talking about Laplace equation and possible solutions of Laplace equation applied to incompressible flow. Some motivation Anderson gives at the beginning. I think it's quite obvious why we need to study aerodynamics and incompressible flow, because only in such a way we can design aerospace structure. It's not possible to design by just our imagination. We need to apply physical law to create an efficient airplanes or flying structures, or at least to reduce possible losses in the flow, to keep energy and to transform this energy in some form we need. Okay, one of the first airplanes you can see here on figure 1 as motivation to study aerodynamics. It's I think there is a polemic about which was the first airplane, because we remember it was Santos Dumont who showed first his airplane in Paris exhibition near to these dates. And the Wright brothers also announced that they have built airplane more or less same time. But people never saw this because it was some kind of secret of a company, right? And Santos Dumont showed it to public earlier. But okay, it's not a problem who was the first. I think that is very important that people started to develop theory, and some parts of this theory that helps us to understand physics and to apply simple laws of aerodynamics we will discuss here in this chapter. Okay, this is a picture of Santos Dumont with his airplane. There's not so much efficient aerospace structure, not so much efficient airplane, just basically set of planes that create significant value of lift. Just because they have a big area, there is nothing, no, not so much developed aerospace shapes or profiling as we have today. And also already in Second World War, or between First and Second World War, aerodynamics received its big advancement and development, because had to create machines that would help to win battles. Such airplanes as we may see here on figure 2, they could be made or projected only with some theories of aerodynamics. Without theories, we cannot do anything. Okay, some picture of modern Cessna 425, one of the probably most beautiful airplanes in small airplanes. Very nice, very efficient and safe. Chapter 3 of aerodynamics is divided in 3 parts. As I already told you, first one is Bernoulli equation. We will touch it today. Since you already know what is Bernoulli equation, it will be not so deep discussion, just applications. And the second part is Laplace equation, which deals with the solution of field of velocities and allows to calculate distribution of flow parameters when Bernoulli equation only deals with point parameters. And then application of Laplace equation in some elementary flows that allow us to develop, when we combine these flows, some theories like flow over cylinder, lifting flow over cylinder, general definition of Kutarzhkovsky theorem, and numerical methods allowing to calculate airfoils or other aerodynamic structures, streamline aerodynamic structures that are used even nowadays, implemented in software like Xfoil. So first, Bernoulli equations. You already know quite well this Bernoulli equation. It's a balance of pressure. Dynamic and static pressure stays constant along streamline or in the cross sections throughout the flow. We know that Bernoulli equation gives us balance of this pressure. We can apply it to obtain change of flow parameters in entrance and exit of control volume, and also be applied to finite element, but not so often. Usually we apply such equation to a big volume where we can determine two sections of our interest, for example, entrance and exit, and in between transformation of flow quantities. And because flow is incompressible, such Bernoulli equation is very simple, can be solved in many different applications. And this equation, as we may see here, number 313, is also dealing with inviscid flow. You might remember that there is also a viscous form of such equation, but in aerodynamics we are not working so much with this form because it can be applied mostly to flow in the ducts, and probably fluid mechanics is the best application of such equation. Bernoulli equation can be used in several applications. We must see that this equation is developed by analyzing the two main equations, momentum equation and continuity equation. Continuity equation can be seen on the bottom of this slide, equation 21, right, which says that the quantity of mass which enters control volume is the same as exits from control volume. Pay attention that in the book we had an error in 5th edition of Anderson book that used as continuity equation. This definition is not completely correct, just a misprint. I would like to note one more time, so you will know that instead of pressure density is used correct version. Okay, already we can find in edition 6 of the book. Bernoulli equation is successfully can be applied to control volume of divergent or convergent duct, where we may find the relation between change of pressure and change of velocity inside this duct, and also can be applied to a nozzle similar to shown on figure 3.7, where we have convergent part and divergent part. Formula which you may see here on right part of the screen describes velocity, which we might be interested to calculate as a function of pressure difference and the area ratio, A1 and A2, in entrance of this diffuser or nozzle and the exit of this nozzle. We may see also that pressure is changing according to Bernoulli equation, right? Pressure is higher on entrance, where velocity is smaller, than pressure drops in the throat, where velocity is bigger and then rises again at the exit of our Pitot tube or Venturi. Such an effect of changed velocity is widely used in measurement of velocity, in not just inside the tube, but also can be applied to other ducts, for example, wind tunnel. Here Anderson shows such wind tunnels and two different sections of, let's say, open circuit wind tunnel is most common type, which is shown on figure 8a. It consists of a pipe of variable duct, and there is a fan at the end which accelerates the flow and creates some flow velocity. And there is a setting chamber which receives flow from outside nozzle, which accelerates flow, and a test section inside which we put the body to test. So inside this test section, it's important to estimate flow velocity, relation between flow velocity and pressure difference, which may be measured easily on such type of tunnel. You can also see on equation on the bottom of the screen. Another type of wind tunnel is closed circuit tunnel. Such a closed circuit tunnel has a duct which where flow is reutilized in such a way we can use some part of kinetic energy of the flow. So such a tunnel will be more efficient with respect to open circuit wind tunnel, where all flow energy is wasted to atmosphere. In case of closed circuit wind tunnel, we do not need so much energy to provide to motor, so such a tunnel can be a bigger size, much bigger size than open circuit tunnel. Usually all big tunnels, I mean tunnels which might have several meters of cross section. I saw the biggest one is near 10-meter cross section. In this section, 10 meter is quite big wind tunnel. They all use closed circuit tunnel because you need smaller energy for such type of tunnel, and the energy you basically apply to such a structure is energy which is consumed by friction, by boundary layer of air friction and the heating of air. So it's efficient. And at the same time, since such structure work with relatively low velocity, Bernoulli equation can be used in calculation of flow properties inside tunnel, inside any part of it. It's quite common, this structure in the world. I think there are tens or even hundreds of such tunnels we might find. Okay. As an example, a test section of such tunnel in United States, University of Maryland, in picture A, and on part picture B is the turbine part. Okay, test section and turbine, quite big, and this turbine is quite efficient as well, so it's not so requires so much power as we might imagine. But still, such a wind tunnel occupies usually one or might be also two buildings, and is significant, right? Unfortunately, at UNB we do not have such a structure, but I hope one day we will have something, at least small scale, that we could use for aerodynamic experiments. Probably many of you know that in our new research building, LDT, that was built recently, had planned space for wind tunnel, but unfortunately, due to some difficult economical situation in Brazil, such a space was not used for wind tunnel and was distributed among laboratories. Okay, here just airplane, just an airplane model to test inside wind tunnel. What is the advantage of a big wind tunnel? That is, you can put bigger scale airplane with many details. You can install several sensors, make good quality measurement, because in such case, geometry can be produced with very, very good quality. So depending on quality of the model will have quality of testing results. So bigger is the tunnel, bigger is the test section, better would be the result of such analysis or such test. Some tunnels that exist in the world, they allow even to put complete airplane, small scale, but real airplane, and or car or an object of relatively big size. What should be the size usually of the body inside wind tunnel? It depends a lot on characteristics of wind tunnel, depends a lot on object. If it's a streamlined body, it can be relatively small, or sorry, relatively big inside tunnel, can occupy maybe near 20% of test section. And if this body is like a blunt body, has a big resistance of flow, can be near 10% occupation, not more than 10%, especially for supersonic applications. Body should be small with respect to area of the wind tunnel. Measurement of airspeed by Pitot tube, shown also in our chapter 3. It's a very simple method. You probably already know quite well. To measure airspeed, we need to have two values. One is called total pressure, which is measured by Pitot tube where flow stops inside, velocity equal to 0 inside such a tube. And so it measures P0 with zero velocity, where all pressure energy all energy is inside pressure, not inside velocity. So we have zero kinetic energy. And the second sensor is parallel. See, the orifice is perpendicular to flow. And in such case, flow does not enter, does not flow inside this tube, and we can measure static pressure at this part. Usually these two types, these two orifices are combined inside one sensor. It's called pitot-static probe, where we can find the total pressure measured at the front point of tube, and the static pressure is measured on side of this tube. Can be one orifice or can be several orifices, depending on structure or model of tube. And then, due to Bernoulli equation, we can find the flow velocity in a very, very simple way. You can see this equation on the left upper corner of this screen. This works quite well for incompressible flow. For compressible flow, we will have different model. Unfortunately, we will need to involve more equations to calculate flow velocity for compressible flow, and for supersonic flow, we will need to involve theory of shock waves, which we will discuss in gas dynamics. So now, just very simple structure, very simple equation to obtain flow velocity or calculate flow velocity, just measuring two different pressures, perpendicular to flow and parallel to flow. Please do not forget, you could ask your questions if you have some questions, or inside comments, or in by voice, or raising your hand now I can see chat and I will try to react your questions if they appear. Very important question is how Pitot tube is designed. There are two aspects, very important aspects in this question. First of all, we need to compensate presence of boundary layer. We need to put holes for static pressure measurement in some distance from tip of this probe, because not just because of boundary layer, but also because distribution of pressure, where in the tip of the probe on the stagnation point, we have raised value of pressure coefficient. So here we cannot put side orifices very close to this tip, because since pressure coefficient is high, the value of pressure is higher than ambient pressure, so we cannot measure ambient pressure. Our goal is to measure P infinite by this side orifice, and by this tip we measure P0. So P0 we measure on the tip where Cp is equal to 1, so flow is stopped at this point, and we can measure. But side P infinite can be measured in two different points. Can be measured here where pressure coefficient is equal to 0. Unfortunately, this zone is having very big gradient of pressure coefficient, so we cannot put exactly. I think it's very difficult to allocate these holes on this position, on this coordinate, but approximately after 14 diameters from the tip, we will have a plateau of pressure coefficient, approximately 0 value of pressure coefficient, where we could allocate our side points with no problem, because this zone is relatively big. Okay, and at the same time, this probe is recommended to have totally 34 diameters. Okay, 34 diameters, and then it has a curvature and goes outside of test section. In such a way, we have 0 pressure coefficient at known region, and we put our side orifices, and we measure exactly P infinite by these orifices. It was one aspect. Second aspect is related to quality of side orifice. You can see it on figure 14 that possible to have different designs. Could be a good design, like proper design, figure C, or could be poor design, figure A and figure B. In case of figure A, since we have such a bad shape of orifice, flow goes around, right, like this, and it creates some recirculation zone and low pressure inside the orifice where we measure. In case of figure B, we have opposite case, right? Flow goes like this, creating this recirculation here, and the pressure inside is bigger than infinite pressure, because we have some flow stopped on this edge, which creates raised pressure or higher pressure than ambient one. And then when we have two edges, parallel, okay, and orifice is having good quality. In such case, we measure exactly infinite pressure. This is very important because depending on this measurement, we will obtain value of velocity. So error of measurement is strictly related to quality of fabrication of Pitot tube. This Pitot tube can be of different size, can be smallest I saw was 0.5 millimeter or maximum 1 millimeter, the smallest one diameter. And the biggest, we can say they can be quite big, can be order of 1 centimeter, for example, the biggest diameter. Small ones are usually installed on small scale wind tunnels where we need to have as small as possible interference or disturbance of flow by this sensor. And the big Pitot tubes are installed in case where structure is big. For example, in the real airplane, we can have big Pitot tubes. They are more reliable. They are resistant to external forces. They are mechanically quite strong and will not be a problem if this probe will be used for a long time, for example, on flying airplane. Nowadays, Pitot tubes are widely used in many airplanes. It's an additional one of tools to measure flow velocity and to measure pressure and altitude. It's one of the additional tools. It's not the only tool which exists in a modern airplane to measure flow velocity, because now we have inertial systems, we have a GPS system, we have other type of ways to understand, to calculate the velocity of flow, velocity of flight. Pitot tubes are usually installed on different positions inside the airplane. You can see here on figure 15, it's on the tip of the wing, as may be seen here. So in such a case, we measure velocity of non-disturbed flow. And also Pitot tube could be installed on the fuselage of the airplane, as you may see here. Just a moment, let me see. Position of this Pitot tube on the fuselage is having a purpose, is the point where pressure coefficient is equal to 0, so we can measure exactly infinite pressure. Such an explanation of position of Pitot tube is shown here. This is a body similar to fuselage shape, or at least, let's say, simulates fuselage shape. And there are 2 points at which CP is equal to 0. It's on the initial part of this curve, corresponding to more or less, okay, somewhere this section, or okay, close to this section. Let me try to make better, somewhere here probably, or at the final part. Also not so good. I will try to make better. The final part of this shape. I think we have a question. If an angle of attack is applied in the Pitot tube, how does it affect the measurement of velocity? A very important question, I think. Just a moment, I will finish with this shape and I will answer this question. So we have this oval body, and installed Pitot tube could be on point on the side of this body, on the front part. On the rear part, we cannot install Pitot tube because it must be directed against the flow, right? The entrance must be against the flow. So since flow here goes in this direction, Pitot tube cannot be installed efficiently, I think so. Front part of the body, and where pressure coefficient is equal to 0, is defined on experiments, defined on calculation or simulation. At this point, if we install Pitot tube, would be the best place. Returning back to question of Guilherme, when we have angle of attack, there is a problem or not? Usually, we can see that the wing is stationary installed on the airplane. So with respect to the angle of attack is almost always constant value. So if we have a main wing, let me draw here on the side. Okay, let's imagine this main wing here. It's not having zero angle of attack. It's already it already has some value, some inclination, okay, but small, as we know. Very small angle of attack. So such a compensation can be easily made when we install Pitot tube. For example, we install this Pitot tube horizontally, or we apply some coefficient like trigonometric function to calculate. But usually can adjust just the position of Pitot tube, I think, and no need to recalculate. I also think that there is a methodology when angle of attack is known and we can apply formula to recalculate pressure coefficient in this case. Do not forget that control of airplane in such case is caused by a flap. Okay, it can rotate this just the final part of this wing. So we are changing angle of attack of just flap part of the wing, not the complete wing. So, but I think it is also possible to provide correction. If we are talking about, for example, testing the wind tunnel and we do not know which is angle of attack, for example, flow is complex. We don't know where flow goes and from where flow goes. So how we can measure velocity in such case? There are several methods. I think one of the most advanced method is when we have a flow or arbitrary flow and we put small dots inside very light particles, small particles, light particles inside our flow, and we track these particles with some system, okay, some hardware system, and by this tracking we can understand about direction of flow and flow velocity. This can be done by modern methods. Nowadays, there are some even methods which doesn't require to insert particles. They track changes in flow structure, like laser methods or slitting methods. I think there are also many different methods. There are advanced methods to measure flow direction. For example, there is a ball sensor, like this ball sensor. Okay, it has a shape of a ball on the stick. And on this ball, we have several orifices, and each of these orifices is connected by a small pipe and measures pressure on this orifice or on this sphere. It's a spherical sensor. It's not just bidimensional, it can be three-dimensional sensor. So, for example, if flow blows from some direction, we will measure bigger pressure at a point close to stagnation point and smaller pressure on point on other part, and very small pressure far, right? We know distribution of pressure in case of sphere is quite well explained. So when our sensors detect such a distribution using mathematical model, we can predict angle of attack and direction of flow. In such case, just analyzing several discrete points where our pipes are installed. So this is how we identify not just direction of flow, but also velocity. So, for example, if this one here measures the stagnation pressure, then other one placed on 90 degrees here, this one placed 90 degrees from the stagnation pressure, we can assume as static pressure. Oh, no, it's a minimal, or could be maximum velocity, could be minimal pressure coefficient, sorry. Maybe CP0 would be somewhere here. But depending on structure and depending on the model, I think, we can predict direction of the flow, analyzing distribution of pressure measured on sphere. Spherical sensors are usually very efficient to understand about flow direction, flow velocity. Disadvantage of such sensor can be only a space which they occupy, because when you have several points, several dots, you need space to put them inside sphere, and it can be bigger than just Pitot tube, right? Can be bigger. The smallest one I saw of such type of sensor was in order of 3-5 millimeters. So such sensor can be really small and measures with a good accuracy direction and the value of the velocity. But different compensation models exist, and I think we can see in future when we discuss flow around cylinder and flow around sphere, there are analytical solutions of flow field around which could be applied to make such kind of compensation which you are talking about, which you are asking about. So compensation is possible, and also adjustment of sensor is possible, and also possible to use such an advanced like spherical sensor to understand about flow field, and without need to adjust sensor, just measuring many points, many different directions inside same sensor. Okay. Okay, you're welcome. Pressure coefficient CP, as we already know, can be rewritten in case of incompressible Inviscid flow. We see in equation 38 CP, same equation as 36, but already applied Bernoulli equation inside. So we change pressure to velocity. In such case, we see that pressure coefficient is a strict function of velocity, depending on velocity on each particular point and infinite velocity, which stays constant. Bigger is velocity, smaller is pressure coefficient, and vice versa. Smaller is velocity, bigger is pressure coefficient. According to this formula, minimum of this function is 1. Oh, sorry, maximum of this function is 1. And minimum of this function, difficult to say, could be probably -3. I think, yeah, such estimation can be used. Then we have the following condition. Conditional velocity for incompressible flow, which opens to us possibility to develop Laplace equation. Divergence of velocity is equal to 0 for incompressible and stationary flow, right? It's because of time derivative for stationary flow is 0, and we can rewrite this derivative right here, and we can open it. And in such case, since density stays constant and inside the derivative will be equal to 0, so only divergence of velocity, these equations, is equivalent to continuity equation. Okay, equivalent one equation, equivalent to another for stationary incompressible flow. This divergence of velocity equal to 0 is an equation which will help us to develop a big variety of analytical solutions, because just analyzing velocity, we can find all flow structure. Just one equation. And now we are going to second part of chapter 3 is development of Laplace equation. Probably you already saw Laplace equation previously in fluid mechanics. I hope so. That Laplace equation could be obtained from definition of continuity equation, which you just saw in the previous slide, equation 39, and definition of potential function phi, which we saw on the previous chapter. I would like to remind you that there is a straight relation between velocity components and potential function. We know that u component of velocity is a derivative of potential function by x direction, and v component of velocity is derivative of potential function by y direction. And same for z direction. I will not use it because usually we have just two-dimensional flow in our applications. But third dimension is also possible. Once we will apply nabla function to, once we will try to submit our velocity definition as a function of potential, we will conclude in equation 340, which is called Laplace equation. When we write this equation in, let me see here, I think now. When we write this equation in Cartesian coordinate system, we will have the following is d2 phi by dx in square plus d2 phi by dy in square plus d2 phi by dz in square is equal to 0. Such a function, and this is an equation in partial derivatives, allowing us to describe our flow in terms of potential function. In terms of potential function, we can describe our flow. So equation 40 is equivalent to equation 39. We just substitute velocity by potential function. And now it becomes the second order equation. Why actually Laplace equation? Why we are transforming our velocity divergence equation inside Laplace equation? What is the advantage? The advantage is that Laplace equation has property which we need to solve complex tasks. First of all, Laplace equation can be used for irrotational flow. Okay, but this is not the advantage. It's just first item is just a statement. Irrotational flow, so flow which is incompressible and inviscid. We cannot use calculation. We cannot calculate flow with a boundary layer, for example, unfortunately. The main advantage of Laplace equation is that this solution of Laplace equation or phi function can be sum or can be added to another solution of Laplace equation at and when we combine such flow, adding one flow to another, we receive more complex solution, and it still will be corresponding to our original Laplace equation. So total of different solutions of Laplace equations will be still solution of Laplace equation. So what we will do, we will elaborate simple flows. We will call it elementary flows, and Anderson also calls it elementary flows. And combining elementary flows, we obtain more complex flows. For example, flow over cylinder, irrotational cylinder or rotating cylinder, flow over sphere. And then we go to see how to create numerical method to calculate flow around complete airfoil based on this Laplace equation. Main property, main advantage, main reason why we're using Laplace equation is written here. Can be written in different forms, as I already showed you before in Cartesian coordinates. can be also written in other coordinate systems, cylindrical coordinates or spherical coordinates as well. In case of cylindrical coordinates is important when we are dealing with the flow which is going around some aerodynamic body similar to cylinder. At least I think that we can consider that leading edge of airfoil is similar to cylindrical body, and then our airfoil can be complete with some linear part. And spherical coordinates we use when we have some body close to spherical shape. Okay. Can be purely sphere or can be ellipsoid in different shapes. We will see in the chapter of three-dimensional flows. Just okay. Another observation that we might see is the following. Last time we also talked about streamline function, stream function. This function xi, which describes as flow, which shows where flow goes, from where flow goes, and to where it goes. Right? And mathematically, we know that when we visualize such flow, we can give different values of this function. This function is b-dimensional function in our case, as you may see from this picture, from these formulas. Okay, and this b-dimensional function in xy coordinate will have several lines of constant value: C1, C2, C3, C4. And the physical meaning of streamline function is the mass flow rate. If you remember, if we have two streamlines, okay, I have 2 points on my streamlines independently where they are located. I have an edge, and I can just subtracting one value from another, for example, C2 minus C1, I will see my mass flow rate from region 1 to region 2. Mass flow rate, how many kilograms per second I have or in my flow. Streamline function is extremely simple, can be written as function of velocity components. In case of incompressible flow is very simplified. We saw it last time. 150 equations A and B. Streamline function has two components, so there are two equations describing it in terms of U component of velocity and V component of velocity. When we receive streamline function as integral of equation 150, we need to analyze both of these equations. We will do it when we see our elementary flows, and you will see how simple can be such integration. Once we have this streamlined function, we can also apply it inside our continuity equation. And we can conclude that we are receiving also Laplace equation. Just take one more derivative from this equation, you will receive also Laplace equation. So as well as potential function df by dx, okay, square plus, just a moment, as well as potential function, streamline function can be also inserted inside Laplace equation. So the form of equation is the same. It's not important which function we are using. We can use inside Laplace equation or potential function or streamline function. Our equation structure will be absolutely same. And you may find a problem here because theoretically solving same equation, we have to find same solution, right? For example, not possible in this case because we know the streamline function are perpendicular to potential function. I will just repeat your picture from our previous lecture, and if I try to build some potential function, it's always perpendicular. Okay, I try to make perpendicular phi1, phi2, and phi3. They are all perpendicular. So streamline functions are perpendicular to potential function. But flow is described by Laplace equation in both of these cases. So why solutions are different for potential function, for streamline function? The answer is even when equation describing flow is same for both of these functions, it's important not just to solve this equation, but also apply boundary condition to these equations. To solve solution of differential equation is a function of boundary conditions. And boundary condition in case of streamline function are different from potential function. Okay, just a moment. Let's have a break. 1 minute. I will take a glass of water and we continue. Please let me know if you have questions. And when I return in 1 minute, we can talk about your questions if there are. Just a moment. Okay, I'm here again. Sorry for this break, but I think I need it because talking 1 hour is not simple and also not so nice today for me. Not my best day. I was even thinking to cancel this lecture, but then decided it would be important if there are some questions to talk. So I was talking about solution of Laplace equation, and that this solution depends only on boundary condition, depends how we set these boundary conditions. There are two different types of boundary conditions which we may find for Laplace equation. They are condition on infinite distance or infinite flow conditions. Usually they can be written in the following way that you may see on the screen. On far field, on far distance from body, we see that flow is having constant value and infinite, and it's horizontal. So u component of velocity is equal v infinite. Okay, and this corresponds to derivative of potential function by x, or corresponds to derivative of streamline function by y. So on infinite distance from a body, we know that these derivatives will be equal to v infinite, and v component of velocity corresponds to 0. It means that our flow is horizontal, not having vertical component. So it has just u component of the velocity, and v component is 0. So it means that if derivative of potential function by y coordinate would be equal 0 at infinite distance, or derivative of streamline function by x coordinate at infinite distance would be equal 0. I think these boundary conditions are simple, right? Because they are just one number and 0 value. Nothing of very complicated. Another type of boundary condition we have is wall boundary conditions, which is more complicated because our wall can be arbitrary. As you may see, I will just go on the previous screen to explain you, because I do not have same picture, I think, later. On the wall, we have from a point of view of streamline function, let's see. This is streamline function. I'm making red streamline function, which touches the airfoil. So this flow which comes to stagnation point of our airfoil, it's split in two flows. One part of flow goes on the upper side, another part of flow goes on the lower side of our airfoils. They go in different points, right, with different velocities. They do not have to meet exactly at the same time moment, because flow path is different, flow velocity is different, so they will not meet at the same time moment again. But these flows will meet. Okay. These flows will meet again, and they will continue to be same streamline. Such a case we may see when there is no flow separation. So we cannot describe, for example, stall conditions. It's not stall condition, it's a relatively small angle of attack. Our streamline split in upper and lower side of airfoil and join again on the trailing edge and goes to infinite distance. So from computational point of view, the streamline is the same on upper and lower side of airfoil. This C is written here. C is constant. C is constant. It means that when we set boundary condition for a wall, we have to use a constant value of streamline. So this is our boundary condition for streamline. Some value. We can even define this value as a reference. For example, in many calculations, even Anderson suggests that we might use C equal 0. It's not important which constant we use. We can use 0, for example, as a reference. So when we have next streamline, for example, here would be C equal 1, C equal 2. It will mean for us that mass flow rate between 0 and 1 is 1, so it's 1 kilogram per second of gas and sector. So it's not important. And thus, in the lower part of this airfoil would be negative, would be -1, C -2, and that correspond to units or correspond to how dense we need to have these streamlines. We can put any value we need. Usually we put 0 because when we integrate, it's easier to integrate 0 than any other value. Because when you integrate 0, you receive 0. So this boundary condition is, I think, natural. Value is the simplest possible. And then we need to see boundary condition for potential function. We know that potential function is always perpendicular. Let me choose another color. Potential function, normal. This is why we have n on this picture here. If we find any point on our airfoil, we will see that we can build this normal direction. Okay, I hope it's close to normal direction. The last line probably not so much. but I will try. Let's assume these blue lines are normal to surface. So and here is the definition for potential function, scalar product of when we transform 48A to 48B, we can see that derivative already. Derivative of potential function by normal direction is equal 0, is for potential function. And numerically, when we say that Xc is constant or streamline function is constant on surface, it means numerically that derivative along the surface is equal to 0 since it's constant. Okay, derivative is 0. And then summarizing, also we can see equation 48, which is streamline on the surface is same as streamline at one at one specific coordinate is constant, can be used for calculation of plane, for example, flow over some surface, and when the surface is not horizontal, we can use some noise here. Sorry. We can use this description of surface to calculate the direction of streamline function. YB by dx is inclination of surface, which you may find, and we see that this inclination of surface, okay, let me see here, this is direction can be split in two. This is dy, and this is dx. And if we see velocity, v, it also can be split. Okay, this infinitely small distance is the same point, but I don't want to put on the same point because then it will destroy all the picture. Relation between components of velocity, v component of velocity and u component of velocity. So this velocity at this point A is same on the upper and lower side. Relation between direction of, or ratio between direction of body is same as ratio of velocity components on the surface. So this is how we define this direction and streamline value on the surface, which is constant. Okay. And the summary. And the summary of our discussion today, that Laplace equation can be written as a potential function phi, or can be written as streamline function xc independently. And we need to define boundary conditions to solve this equation. Right. I hope we already understood which are two types of boundary conditions, on infinite distance and on the wall. And solutions of such Laplace equations form a sum of elementary solutions or elementary flows that we will discuss very, very soon. From solution of Laplace equation, we obtain phi or xc function, and after we obtain velocity components, just taking derivative of streamline function, we obtain u component of velocity, and another derivative we obtain v component of velocity. This is if we are solving in terms of streamline function. If we are solving in terms of potential function, velocity components, after we solve Laplace equation, could be found in a very similar way. You can see right here. Okay, so we take derivative of our solution in x direction, obtaining u component of velocity, and we take derivative of potential function by y direction and obtain v component of velocity. The main task for us is to solve Laplace equation with known boundary conditions, and then we obtain velocity components by taking derivatives, and at the end applying our velocity components to Bernoulli equation, we obtain pressure distribution. So in schematic, we will we may write the following: that first we obtain phi or c, or potential function or streamline function, then we obtain u and v components of the velocity, and then we obtain v vector as v in square is u in square plus v in square in a such way. And then after we obtain vector of velocity, we obtain pressure distribution. And this is all we need to know for incompressible flow. Okay, for incompressible flow, density is constant, so is not the parameter that we are searching. Density is constant for all the volume. Okay, I think our today lecture should not be very long, because I would like to start and usually start talking about elementary flows at a new lecture. So I would like to hear if you have some questions about today's subject or previous subjects, or task 1 that should be delivered end of next week. By the end of next week, let me know if you have some questions in the chat. I'm expecting, and if you remember, we agreed to define, if we meet tomorrow, if you have questions about work 1 that should be explained tomorrow, or you already found all your answers in my previous videos or our previous lectures. So I'm waiting 1 minute, 2 minutes. Please write or say by voice if you have these questions. And also one thing that worrying my monitor, he said that no one asked for help yet. So please do not forget that we have Artur working as monitor, and you could always ask him about aerodynamics, some problems of doing works. I think it's important because Artur is already many semesters my monitor in aerodynamics, and he knows perfectly. And he is the guy who is doing a small wind tunnel as his TCC. Small open wind tunnel we are constructing. I hope it will be ready. It will be ready in 2-3 months before end of this semester, and then from next semester we can arrange organizing some experiments inside such a small wind tunnel, visualizing and measurement of at least characteristics of wind tunnel. Very big work, very interesting work. Tunnel will be not so huge, but if you have just one person who is working on this, it's a huge work. It's a huge work. Okay, I'm expecting your question. Please let me know. I think write me if you have some question. So I see no questions yet. And if there are no questions, we can finish for today. Please do not forget what I told you. You always can help of me, of monitor, can see videos on all the questions. I hope it will help you a lot making work one of a good quality. So I would like to wish you a nice weekend. We will not have class tomorrow because no question appeared. There is nothing to talk, and have a nice time. See you next week, probably, I hope. Goodbye, guys. Thank you for participation.